next on stage is Gabel. He's at the moment, a freelancer, software consultant and trainer, a programming junkie and computer history aficionado. Tomer's been a vivid software professional for almost 2 decades, during which he's built many number of predominantly back-end systems, co-founded 2 major Israel user groups, organized an annual Scala conference, and is a recurring speaker at software conferences, including Build Stuff. Applying made his trade as a gun for hire at Substrate. He secretly still hopes to realize his childhood dream of becoming a lion tamer. Okay, and he's going to talk about software architecture, and so be ready to ask the questions. If you have any, please write at Pine. Let's try to do that. And let's welcome Tomer. Tomer, off you go. A round of applause for Tomer.
Yay, thank you. All right, so although I can't see any of you, I want to tell you this is awesome. This is the first software conference I've been to in 2 years, probably the same for most of you. It feels kind of like a reboot, doesn't it? Like, you come here, you either give a talk or see talks, so everything feels a tiny bit different. Did the sound just change? Well, let's get started. So, what we're going to be talking about today is software architecture. This is going to be more of a philosophical kind of talk. So if you're hoping to get some ideas for your next actual architecture, this is probably not the right room for you, and I'm sorry. And if that's the case, then feel free to leave. I'm not gonna get offended. Actually, I'm not even gonna see you do it because this is really bright. So, first things first, let's start with finding out just how awake you are. So a little bit of audience participation. Please put your hands up in the air if you agree with the following sentences. Number 1, an architect draws diagrams. All right, that's more hands than I expected, about a third. Let's try another one. The architect owns the database schema. No hands. Wonderful. The architect is a very experienced senior developer. Yeah, that's about half. And finally, an architect doesn't write code. Well, there's 1 or 2 hands there. I think, hopefully these are just people trying to rile everyone else up. Okay, so that gives us some data points to start with, and let's do that. The context for this talk is just a realization that although especially over the last 2 decades, the systems that we've been building have been getting way out of hand, way more complex. So if you compare the sort of code, the sort of systems that you're building today to the ones you might have been building 5, 10, 20 years ago, you'll find that the systems we build are more complex in every dimension. They generally handle a great deal more data. They are beholden to much higher standards of latency and availability. They just do more stuff, right? The products we built today just do more than they used to do 5, 10, 20 years ago. So complexity is sprawling out of control in literally all dimensions. And it turns out that taming that complexity is really, really hard, which is why virtually every software company you've ever seen ends up hiring system architects. We all need them. But it turns out we can't really agree as an industry on what system architecture is, what system architects do, how to find them, how to hire them, how to measure their success. We don't do any of these things properly. And it is my purpose to take a stab at it and add a little bit of context that will hopefully maybe help us make sense of what software architecture actually is. Now, crucially, we're not going to be talking about these bottom 2 things. We're not going to be talking about success criteria or retention, because I believe these are artifacts. I believe these are obvious logical extensions for when you actually know how to answer that first question, which is, what is software architecture? What is a software architect? What is the role? What is the purpose of that organizational function? And we're going to start with asking the obvious question, which is, what is software architecture? Now, it turns out if you do a little bit of research, if you start Googling away and you start reading the literature, you start reading opinion pieces that people have written about what architecture actually is, you're going to find very, very few commonalities, and you're going to find very few concrete, workable definitions that you can actually make sense of. So let's take my top 3 picks. The first is software architecture is the set of design decisions which, if made incorrectly, may cause your project to be canceled. A little funny, kind of true, you can't argue with that. However, it's not very actionable because at the point where your project is canceled, you've already made those decisions, right? That's a kind of retroactive definition of what software architecture decisions are. So it's not very useful. The second one harkens to today's keynote, and it's from Grady Booch. Architecture represents the significant design decisions that shape a system where significant is measured by cost of change. So basically what he's saying is he's actually offering us a much more actionable definition. If you start with a decision and that decision turns out to have been the wrong decision and costly to change, then that was an architecture decision. But again, not very actionable because it's also retroactive. You don't actually know the cost of a change until you have to make that change, right? So it doesn't really help us make sense of it either, but at least it alludes to a, shall we say, economic model of dealing with software architecture. If it's costly and it's important, then it's architecture. Not great, not terrible. The third definition is the one that is probably the least useful of the bunch, but it's the one I love the most. Architecture is about the important stuff, whatever that is. Right? That's a great definition that I'll just leave you to consider. Now, if you continue Googling and you try to figure out what a software architect does, what is the function of a software architect, things get even murkier. I've only managed to find 2 quotes that work for this. The first is, an architect is someone who knows the difference between that which could be done and that which should be done. And that's a quote from Larry McVoy. Now, again, not very useful, not very actionable in and of itself, but it does allude to something that I think all of us have come to expect from the people that have that title of software architect, which is we expect them to have taste. We expect them to make discerning decisions. We expect them to actually look at the solution space to a particular problem and be able to choose among the various solutions in a way that is tasteful, in a way that resonates with the rest of the team and that carries the company forward. Again, not particularly actionable, but there is some grain of truth to it. The second one is the most concrete definition I've found from the role, and that's from Wikipedia. A software architect is a software development expert who makes high-level design decisions or choices and tries to enforce technical standards, including software coding standards, tools, and platforms. Now, what I love about this definition is that I disagree vehemently with literally everything, every part of that sentence, except one, tries to. At least they were honest, tries to enforce. But really, does anyone here agree with this definition? I mean, raise your hand if you do. It's perfectly legit. I just have my own one opinion. All right, so we do have a few hands. Fair enough, but I would argue that this is patently untrue, and I'm going to try to make that point over the next 30 minutes or so. We do have some set of agreements on what things aren't. So we all agree, I think, that architecture isn't in and of itself process, diagrams, and documents. Architecture is often expressed in diagrams and documents, but diagrams and documents are not architecture. They're not the desired artifacts of a software architect. They're just things that sometimes happen, that used to happen so often that people just kind of developed a reaction to it. If you see someone putting together UML diagrams, your instinctive reaction is going to go, that's not architecture, that's bullshit. Pardon my French. We also agree on what an architect isn't. So we actually do have some agreement in the industry on what we don't want our architects to do. So contrary to a couple of fingers that people put up in the air earlier, I think largely the industry has converged on an agreement that you cannot be a competent software architect without having at least been and probably still being a practicing software engineer, a practicing programmer. We also know that architects should not be gatekeepers because the horror stories around architecture review boards and architect teams that sign off on designs abound, right? Everyone has those horror stories about a perfectly sound design that didn't make it through an architecture review board, or that they had to fudge it so that it goes through and then build it the right way anyway. So gatekeeping is not the point of a software architect. A software architect is not someone who necessarily owns the architectural decisions. And management, right? A software architect doesn't necessarily have to lead the team. They don't necessarily have to lead anyone. They don't necessarily have to manage anyone. And the reason for that is because the skill set, which we will circle back to, the skill set required to be a competent software architect has as little overlap with management as software engineering does. Software engineer and a manager do not have overlapping skill sets by much. SREs and developers have overlapping skill sets, but not entirely. So these are separate disciplines, right? Management has nothing to do with architecture. So what's amiss, right? We have, this industry has been around for, 70 years now, and we still don't have an even remotely coherent definition of a function so vital and so critical that literally every software company in the world that grows starts hiring for it. I would like to propose one way of looking at it that is, I will say this right in advance, it is wrong, but it is instructive. And that is, if you consider all of the parts of your system, everything about your system that does not deliver immediate business value, right? The things in your system that deliver business value are the pieces of code, the components you write that actually do the thing your customers need you to do. Everything else is support. Everything else is substrate, right? Your compute substrate, your servers, your cloud provider, your operating system, your container structure, whether you use Kubernetes or not, your service substrate, so whether you use Rabbit or Kafka or whatever, your logging system, metric system, all of these things do not directly deliver business value. However, all of these things are functioning pieces of your system that are on the critical path. You cannot deliver your business value without your cloud provider or whatever it is you're running on, right? But these are what used to be called non-functional aspects of the system, which is a terrible name. But is this architecture? Well, some of it is. Some of it is definitely what you would consider to be part of your software architecture. Your messaging system, for instance, that's a classic. Indeed, some of the first architectural decisions you will make about your system revolve around where is it going to be hosted? Is it on-prem? Is it going to be on a public cloud somewhere? Is it going to be running on Linux or Windows? Is it going to be .NET or Java or Python or any of these things? These are very, very fundamental decisions that you make right out the gate. So some of it is clearly architecture, but this list also mixes in way too many disciplines. So you have your ops people, you have your QA people, you have your IT people, you have very, very different disciplines that are all embodied in this very small list of stuff that is not delivering business value, but is on the critical path of your system. And it also misses a few key points. So I want to show you 3 diagrams, because diagrams, as we will talk about, do represent our useful tools for developing system architecture, although they're not actually the architecture. So here is one example. We have here a system diagram of a particular product. Let's call it product X. There are various bits and pieces there. There's a server, there's components, there's third-party components, and this diagram kind of shows how they interact. So this is an architecture diagram. Next, we have a completely different diagram. And this is also an architecture diagram, but this one actually reflects the architecture of the data architecture of a particular system. So you have a whole bunch of components here. You have MySQL, you have different zones, specifically on AWS, but it doesn't actually matter, right? You have different data centers, you have replication strategies between them. You'll notice that this diagram doesn't have one word that tells you what the product is. And yet, I believe, everyone in this room looking at this diagram would at least consider it to be a system diagram or an architecture diagram. And then we have the third one. So this is from SQLite. This is the SQLite architecture diagram from the SQLite documentation site. Right? You'll notice there's no servers, no data centers, no third-party components. All of these things are components of an in-process system that it doesn't even have an executable. You embed it in your own executable. And yet it has architecture. Right? All of these things are architecture. So, what is my point? My point is that architecture is contextual. Architecture is the thing that becomes visible when you take your system and start looking at it from different perspectives and you zoom in and out, and the way things are put together starts becoming as important or more for the purposes of the architect than the components that comprise it. Architecture exists in all software. Architecture exists whether you have a single process running somewhere, whether it's a library, whether it's a clustered system, whether it's a data center, it doesn't matter. Whatever piece of software you're building, whatever the scope of it, the scale of it, there is architecture in it. Because architecture has to do with the interstitial parts. Architecture has to do with how you put the moving parts of your system together, as opposed to how you actually implement every part of that, every moving part of that system. As a side note, architecture can also be emergent, right? You, generally speaking, for any software system that you might design, you either plan for your architecture, which is hard, you kind of arrive at an architecture and then retrofit new architecture into your existing system, which is crazy expensive, as any of you who've tried to do that would know. Or you can kind of stick whatever it is on with duct tape and hope things don't blow up, which they will. But most critically, the point I'm trying to make is that architecture is all about layering. Architecture is about how you take all of the different things that comprise your system and you figure out how to layer them on top of each other in a way that is coherent and that makes sense. So let's see some examples of good and bad architecture, see what we can learn from them. I want to start with something that all of you know and probably most of you love, which is Unix. Unix, the Unix philosophy, and specifically I want to talk about Unix pipes. So let's start with what the Unix philosophy is for this context. And I just picked a random abridged version from the internet. I think this is probably the most well-known expression of the Unix philosophy, which is whatever your program does, you write a program that does one thing and you do it really, really well. You write programs to work together, and you write your programs to handle text streams so that the input and output of your program is a text stream, because that is a universal interface. Now, there's a lot of criticism around this, especially with respect to that text being a universal interface part, but it stands the test of time. Unix is, what, almost 50 years old now, maybe even exactly 50 years old now. Right? That is a fairly long time for a piece of software, for a philosophical stand for a piece of software to actually survive the test of time. Not only that, the Unix philosophy actually outgrew Unix. We take the same set of principles and we apply them to our modern day software stacks. We write microservices, right? Write a service that does one thing, has one area of responsibility, does it really, really well. You write your services to work together, and you write your programs to handle, well, not text streams, but something very akin to it, which typically would be like JSON over HTTP or something. That is a private case of a text-based interface. So I would assert that this approach, and this approach is architectural in nature, is very, very successful. And I believe that this approach is epitomized in Unix pipes. Pipes, you know, the pipe symbol that you type into your terminal 25 times a day. Pipes are all about composition, and pipes are tremendously successful to the point where we still use them today in virtually every operating system that you'd use, whether it's Windows, Linux, Mac, it doesn't matter. You use pipes because pipe is a very, very simple concept. You have process A, you have process B, and then you have a byte stream between them that they communicate over. That's it. That's the whole concept. So why was it so successful? Well, byte streams can carry anything, right? Despite that assertion about text being a universal interface, there's nothing about Unix pipes that actually forces you to use text. You could cat a binary file and pipe that into curl to upload to an S3 bucket somewhere or something, right? So it's a byte stream. It can carry literally anything. Pipes picked the atomic unit of data in modern day computing and just use that. It's a stream of bytes. You put whatever you want on top of it. It doesn't imply text. It doesn't imply structure. The reason I think pipes have been so successful is that they only deal with one layer. They have very, very coherent boundaries. You have a process, you have a process, you have a byte stream. That's it. Everything around that is not a pipe. That's a different layer of the stack. Find a different solution for it. So critically, pipes do not introduce any constraints upstream or downstream. Once you have two processes communicating over a byte stream, pipe is done. It doesn't care if you emit JSON. It doesn't care if you emit binary data. It doesn't constrain you in how you compose that into a bigger system. And that is tremendously powerful. Let's take a look at another example. Kafka. Kafka is a newish product, and yet it took the world by storm. So if you recall the world pre-Kafka, if you ask yourself the question, why is Kafka successful? Let's compare what was out there to the world post-Kafka, if you will. Basically, when Kafka came along, what you had is a whole bunch of pub/sub style systems, basically messaging or queuing systems, where RabbitMQ is just a canonical example, right? It's not the specific product that I care about. And at first glance, it doesn't appear that Kafka has any advantages over RabbitMQ. The ease of use of Kafka is Kafka certainly isn't as easy to use as RabbitMQ. The operations of Kafka are tremendously more complex than the operations around RabbitMQ. And yet, Kafka doesn't seem to have that many features compared to RabbitMQ. So why was it successful when the world already had a product that ostensibly solved a similar problem? The reason is that they don't actually solve the same problem. And we'll circle back to that in 1 second, but critically, I want you to pay attention to the fact that a pub subsystem like RabbitMQ is a queue. Right? You have a message coming onto the queue. It's removed from the queue by the consumer. Done. That's a very small set of semantics. Whereas with a lot of systems that you build, you want features like being able to replay messages. You want to be able to publish messages so that multiple consumers can actually consume those messages. Now, before Kafka, what you had is something called an enterprise service bus. And if you're wondering what my opinion is on how an enterprise service bus looks under these, how it behaves for these traits, you don't have to think hard because it's basically this. If you use an enterprise service bus or try to build a true messaging platform where service A produces events that any number of services can consume, you try to use an enterprise service bus or any of the products in that space, you're in for a very, very painful time. And the reason is that pub/sub doesn't do enough for the purposes of our systems. And enterprise service buses do way, way, way too much. So an enterprise service bus not just carries your messages from service A to services B, C, and D. It also lets you have third-party integration points. It does data transformation and data aggregation, and it's stateful in some cases and not stateful in others. It has a lot of different features. And it turns out that having those features means that an enterprise service bus does not have what I would call coherent layering. It does not solve a coherent set of problems, and therefore it introduces a lot of different constraints both up and down the stack. Kafka, on the other hand, got the layering just right. Kafka gives you a distributed log. Done. That's all it is. That's all it does. It doesn't purport to give you anything else. I think the biggest feature Kafka has that is not just being a distributed log is around compaction, and it's a feature I never found cause to use. So it solves a much more rigidly defined problem. It solves one problem in one layer of the stack. It doesn't purport to do anything else, and therefore it doesn't constrain you in how you use it. It doesn't assume that you're sending JSON or XML or whatever it is that your enterprise service bus used to assume. It doesn't assume that you connect it to any variation in a theme of a third-party system. It just gives you a distributed log, producers, consumers, that's it. It's coherent. So what do these systems have in common? So if you take pipes, queues, distributed logs, if you take these very fundamental concepts when you're building your systems, they have a few things in common. Critically, they're very, very simple concepts, and they're very easy to explain. If you have a system that provides queuing, you should be able to describe in 1 or 2 sentences what queuing is and what a person building on top of that needs to know. That is not the case for an enterprise service bus, but it is the case for pipes or Kafka or RabbitMQ. There are simple concepts that are very easy to explain. And therefore, they have very limited surface area, right? And we know that having concrete boundaries around our systems, whether it's from DDD, whether it's encapsulation and object-oriented design, whatever angle you arrive at this from, coherent boundaries are super critical in understandability of a system. And when you don't have coherent boundaries, that's when things go awry. That's when people that build on top of these systems make mistakes, because they have to either understand the deeper layers, or if they can't understand the deeper layers, they're just gonna make assumptions about them and then make mistakes and cause constraints further upstream. As a counterexample, to sort of drive the point home, and this is going to be a little bit contentious. I'm sure a lot of you use these technologies here, and I apologize. I do not mean to denigrate your technology choices, but I will say that ORM is a huge anti-pattern, and I'm going to use that as a counterexample for a shitty architectural pattern. So, in ORM, object relational mapper, it doesn't matter what ORM you use, they all have the same basic premise, which is they understand objects, class hierarchies, whatever it is your language gives you on the one hand, they understand databases and database schemas on the other hand. And in order to map one to the other, any ORM would have to both integrate with the underlying virtual machine implementation, whatever language it is you're constructing on, in order to provide things like walking over relationships or lazy loading of properties or any of these things. Your ORM has to actually integrate with the object system behind the scenes. Also, an ORM, in order to give you those same features, in order to give you transactionality, in order to make sure things are coherently and consistently updated in the database, they also have to integrate very heavily with the database. They have to manage transactions, so they give you a transaction manager, right? That's an awful lot of stuff for just for a solution that purports to only solve a simple problem, which is I have objects in memory, I have the database, and I want to map the two. Right? That is a fundamentally problematic assumption that you can solve that problem without touching all of these different layers. Now, why is ORM bad? Well, to my mind, ORMs are bad fundamentally because they try to couple two very, very different concepts. Objects in memory do not look anything like objects on the database and should not be directly mapped. That is more of a philosophical point, so let's ignore that for a second. ORM is bad because it is very easy to get started with it, and once your system hits production, starts growing in all of those scaling dimensions that we'd mentioned earlier, debugging issues with an ORM can be very hard because it touches all of those different layers. If you're trying to figure out why you have a very, very slow query and you don't, you can't look at the query and go, oh, okay, that's stupid, I'm missing an index, right? That's not the sort of problem I'm talking about. If you have a query generation problem or a transaction scoping problem or any of those things that you hit right out the gate as your production system grows with an ORM, debugging it can be a pain. Scaling it is an even bigger pain. And crucially, there's lots of little pitfalls and lots of nuances in how you're supposed to use your ostensibly pure object model when it is getting mapped by an ORM onto a DB schema and vice versa. There are things you shouldn't do on a database when you're working with an ORM, and there are things you shouldn't do with your object structure when you're working with an ORM. And I believe the reason is because, again, ORMs attempt to operate at many, many different layers at once, and crucially, the whole point of an ORM is to blur the boundaries between two very distinct layers. You have your class hierarchy in memory, you have your database. Those are very, very different things. The whole point of an ORM is to make those two things look similar enough that you can use them interchangeably in your code and not worry about it. And it turns out that doesn't work very well. So, quick recap on layering. We want coherent boundaries. Coherent boundaries around layers, coherent boundaries around components give us simplicity, they give us understandability. Okay, simplicity means it does very little. It does what we need it to do. Understandability means because it does so little, I can understand what it does in full. I don't care about the details of how it's done as long as it's all within that strong boundary that I can actually reason about. And then there's precision, which is to say that if the thing says that's what it does, that is what it does and nothing else. There are no unexpected issues around transaction management, for instance, with an ORM. There are no unexpected out-of-order messages coming through in RabbitMQ, right? That's precision. It's the fact that the tool gives you boundaries that you understand well enough and it doesn't surprise you. If we have coherent boundaries, we get systems that are very easy to improve because you end up with, your improvement ends up being inside of a boundary. As long as you respect the semantics of that boundary, as long as that boundary is held, then no one else should care. It also gives us systems that are easy to extend with additional components, and it gives us low friction. And the reason for that is because once you have strong boundaries, those boundaries are respected, everything that happens outside of those boundaries has no effect on what happens inside of those boundaries. So if you have a system that's built with an ORM and you try to add new models to the mix, or you try to, for instance, take a few of your models and separate them to a different database, or you want to introduce partitioning, or any of these things that should be possible, they should be possible with an ORM, they turned out to be dramatically difficult with an ORM typically, again, because of that lack of coherent boundary between the different layers of your app. So this is what we want. We want simplicity, understandability, and precision because it gives us those values. So can we actually take all of that reasoning and do something useful with it? Well, generally speaking, we define any discipline, whether in software or anywhere really, by its outcome. So if you are a programmer by trade, if that is your function, then the desired outcome is an implementation of the software system, right? It is code that is obviously tested and reviewed and all that stuff, but the desired outcome is code that meets the business needs. That is your job. If you are in QA, modern QA, not the QA of 20 years ago, then your job is to provide the cognitive framework, the tools, the know-how necessary to assure quality in the product. That is your job. If you're in operations, then it is your job to provide the means of actually getting to a field deployment of the system and operating it, right? You build the tools, you build the monitoring systems, whatever it is that's needed to actually reason about, get the system in the field and reason about it. If you're a product manager, you manage the product, right? You manage the complexity of the product. What is the desired outcome of a software architect? Well, if software architecture is about layering, which I believe it is, and good layering is about getting to coherent boundaries, then I believe we can actually come up with not a brilliant deductive definition of what software architecture is, but one that is like one iteration better than what we have today. And I believe that this is what it amounts to. Software architecture is obviously about meeting the present needs of the system, right? That's a given. Without that, then your architecture sucks and you should be fired. But critically, while not constraining future decisions, which means that the job of the software architect is, in fact, to minimize the impact of the decisions you make today on the future evolution of your system. Every decision you make today is going to add constraints. If you pick Windows as your operating system of choice, that means you are constrained to run components that are Windows-centric. You are constrained to use operating tools, deployment tools, whatever, that are Windows-centric, right? That is obvious. What is less obvious is that decisions you make today can affect your system in the future, even when they're not architectural decisions, even when they have nothing to do with third-party components. So just to give you a really like bare bones example, let's say you have a production system that you're building. It has a database, and the database are users. So you have a user entity. Every entity in your system has to have some kind of ID. What do you pick? Do you pick a auto-generated sequence number? Just 1, 2, 5? That it seems to be a perfectly logical choice for many systems. Maybe you should use a GUID, like GUID, a globally unique identifier, a random ID of some sort. Also a perfectly logical choice. Maybe you should take a third-party ID generator service, like Snowflake's ID generator or whatever. I don't know, maybe that's a reasonable alternative. But critically, every decision that you'd pick would have some different set of constraints in the future. And the only way to arrive at a good architecture is to be able to reason about those future constraints. So if you pick an auto-generated sequence number, well, that's great, but there is nothing you can do that will prevent downstream components in your system, the developers developing on top of that user service, from assuming that if it's a sequence number, then I can actually reason about the ID. I can actually take user ID 1, user ID 2, compare them, and make certain assumptions about what user IDs being sequential, for instance, means. Right? If user 1 was created right before user 2, maybe that means something. And once I picked an auto-generated sequence number, there's nothing I can do to prevent a downstream user from making use of that assumption. So on the other hand, if I picked a GUID, I did enforce that assumption no longer exists, but I've also enabled potentially the system to become partitioned in the future very, very easily, because it's just a GUID. You can generate it anywhere. So any decision that you make today, even something as small as what kind of an ID to pick for my entity, will have some constraints on the future evolution of your system. Now, in order to reason about that, in order to actually do the job of system architect, you have two core skills that you need. You need to be able to interpolate very well, and you need to be able to extrapolate very well. To interpolate very well means you need to be able to look at a particular problem, a particular set of constraints for the problem that you're attempting to solve, and the solution space for those same problems, and make reasoned choices. Right? You need to pick a solution that is fit for purpose for the system that you're building. That is what I call interpolation. And that is sort of the thing that most people perceive as the job of a system architect. And it is part of it. But I think the other side of the coin, which is being able to extrapolate, is that much more important. And extrapolation means you, as a software architect, it is your job to think of all those future use cases, not because they are important necessarily, but because you have to ascertain whether they are important. So if you make a decision today that will make your system not be scalable to, for instance, a cluster in the future, because it's convenient for you, that might be a very, very good decision. But the only way you can say that it's a good decision is if you had asked, do you realize that this decision means we cannot move from a single host to multiple hosts in the future? Is this acceptable? Do we as a business care about it? Is it a product decision that we even want to go in? Right? Asking those hard questions is the job of the software architect, and pointing out those far-flung ramifications of decisions today is the job of a software architect. Now, critically, picking good solutions to problems is a skill that can be taught. It is a skill that is taught, right? Even in universities, we train people on basics of the available solutions that are out there. Even at university today, you will come across architectural patterns and architectural tools, whether it's microservices, whether it's Kafka or any of those systems. You're liable to run into them. We train people on those types of solutions. But also you can read postmortems, you can read blogs, you can attend conferences to learn about new architectural patterns, right? So the solution space that's out there for all sorts of problems is something you can explore irrespective of anything else. It's something that you can teach people. It's something that you can learn as you go. Extrapolating, knowing that a particular decision will have unintended future consequences for the system, for the organization, is a skill that can't be taught, but it can be learned. And predominantly, it is a skill that is learned from experience. The only way you're going to know that any one decision will have future ramifications downstream is that generally you can tell that by one of three ways. Having seen it before, that's experience, and that is why most of you seem to agree that a software architect does have to be a very experienced, very senior software engineer, because that is where this experience comes from. That is where the ability to say, this could be a bad idea in the future, and here's why, let's make a reasoned decision here, that comes from experience. It also comes from introspection, just thinking really hard about the ramifications of things. But I think we all love to ignore that third thing, which is aptitude. I'm of the opinion that software architecture is a discipline. It is vocational. It is not fundamentally different in that respect from ops or management, or if you are a practicing software engineer, maybe you have an affinity for developing lovely looking front ends, or maybe you don't care about the way that it looks, but you just love building large, complicated systems that deal with a lot of data, and you love to be in the back end. In all cases, you're a software engineer, but you have a different vocation. You have different aptitude. You have different preferences, different passions for things. I believe being a software architect is not something you can grow into. It is not, you don't advance from being a software developer to being a manager. We all know at this point as an industry that is just wrong. That is not a career path. That is just sticking people that don't necessarily need to be there for the sake of advancement. I believe it is the same with software architecture. You don't get to be a software architect by becoming a senior or more senior engineer. You become a software architect by architecting, by having an aptitude and a passion for solving these types of problems. You have an aptitude for picking solutions that are fit for purpose, which in that respect, you're no different from any other software engineer. You just generally apply those decisions elsewhere. But in order to be a really good software architect, you need to have an aptitude for taking a decision today and seeing where it could have an effect in the future. You need the experience to inform that, but you need the aptitude and the passion to actually make those forecasts. And that is something that I don't believe can be taught, but I don't think it's something that you need to worry about either, because if you're not passionate about making those determinations, just don't be a software architect. Do something else. Do something you are passionate about. And that is really my main point. Software architecture is about layering. Good layering is about coherent boundaries, and being able to say that a decision today is not going to screw you over royally 6, 12, 36 months down the line, and how it could screw you so that you can have a reasoned discussion around that is the job of a system architect. So before wrapping up, I will just point you to This is the whole point of the talk. I believe it is the primary role of a software architect is to avert future constraints on the system, is to make decisions today that will allow the business to make completely and radically different decisions in 3, 6, 12 months, whatever it is, and be able to make those decisions in spite of the way the system was put together in the first place. And that is the primary role of a software architect. And with that, we are out of time and I'm out of slides. So if there are any questions, I will take them. And otherwise, thank you very much for your time.
I see there are no questions at Pine. Do we have any? Okay. Let's hear one question and then off we go. Yes.
I guess we agree that being able to draw diagrams is not like equal to being architect. It's not part of being an architect. But what about being able to write good messaging contracts? Because then we're defining boundaries and layering. So should architecture be good at that?
So just to repeat the question, because for the people...
Now we heard it, since we shared the microphone.
Okay, so that's not a problem anymore. Cool. I would say that if the set of decisions you need to make today also include messaging protocols and messaging contracts, then yeah, that is the job of an architect. Not because that is just the job of the architect. You need your programmers to be involved in that too, but because the protocol that you use for messaging between your services is exactly the sort of thing that will have very, very far-reaching implications for your software in the future, which is why even outside the context of architecture, when microservices sort of came into vogue, there was a lot of discussion, especially in conferences and such, for instance, around how to do API versioning correctly, how to do what essentially is a version of schema evolution for APIs. How do you maintain an event schema that you publish onto your Kafka or event bus, whatever, in a way that you can still evolve that. And that is what makes it an architectural decision. It's the fact that it's a small technical decision today. I mean, it's not hard to get two services to communicate in a coherent way. What is hard is getting them to communicate in a coherent way that will remain coherent despite the system undergoing evolution over time. That is, in my opinion, why, yes, that is part of the job of a system architect involved in that type of system. It's not because it's a contract. The fact that it's a contract doesn't mean anything. It's the same principle as you have a method declaration, right? It's not fundamentally different, except the long-term ramifications are a lot greater because the data outlives the process that created it. So you have to find some way to make sure that the data remains useful and usable and evolvable over time. And that is what makes it an architectural question. I hope that made sense.
Yeah. Thank you, Grady, for your question. Thanks, everyone, and thanks once again, Tomer. A round of applause for Tomer for his presentation.
Thank you very much. Cheers.